When I talk about dark energy and cosmic expansion, I like to start with something very concrete: the sky itself. If you go out at night and look up, you see stars, maybe the Milky Way, maybe a faint smudge of a nearby galaxy if your sky is dark enough. It feels static. It feels like a backdrop. But on large scales, that picture is wrong. The universe is not static. Space itself is stretching. Galaxies are moving apart. And the rate at which they move apart is not just changing, it is accelerating. That acceleration is what we call dark energy. I want to unpack what that means, how we know it, and what it might tell us about the fate of the universe. First, I need to separate two different ideas: motion, thrace, and expansion of space. If you throw a ball, it moves through the air. The air is the background. It is not growing. That is motion in a fixed space. Cosmic expansion is different. Imagine dots on the surface of a balloon. As you blow up the balloon, the surface stretches. The dots move apart, not because they are walking on the surface, but because the surface itself is expanding. In cosmology, galaxies are like those dots. On very large scales, galaxies are mostly carried along by the expansion of space itself. We describe this expansion with a function called the scale factor, usually written as AT. Time t is cosmic time. The scale factor tells us how distances between faraway galaxies change with time if we ignore their small local motions. If AT doubles, then the average distance between galaxies doubles. The rate at which A at t changes defines the Hubble parameter, h at t. Today we call it h0, the Hubble constant, although it is actually slowly changing with time. The basic observational fact is this: the farther away a galaxy is, the faster it appears to recede from us, with a speed roughly proportional to its distance. That is Hubble's law. How do we know that? We measure distances, and we measure redshifts. Distance is hard in astronomy. We cannot stretch a tape measure between us and a galaxy millions of light years away. Instead, we build a ladder of methods. For nearby stars, we use parallax. The Earth orbits the Sun. That gives us a baseline of about 300 million kilometers. As we look at a nearby star from different points in Earth's orbit, its apparent position shifts slightly against the background of more distant stars. That shift gives us the distance through basic geometry. This is the foundation of the distance ladder. For more distant objects, we use standard candles. These are objects whose intrinsic brightness we think we know. If we know how bright something really is, and we measure how bright it appears, we can infer how far away it is, because light spreads out as it travels. A key standard candle in cosmology is the type Ya supernova. This is a kind of exploding star that reaches a peak brightness that is quite uniform after we apply some corrections. By calibrating these supernovae using closer objects whose distance we already know, we can push our distance measurements out to billions of light years. Redshift is the other ingredient. When light travels through expanding space, its wavelength stretches. Longer wavelength means redder light, so we say the light is redshifted. We can measure this by looking at spectral lines, the fingerprints of atoms and molecules. In the lab, hydrogen emits light at specific wavelengths. In a distant galaxy, we see the same pattern, but shifted to longer wavelengths. That shift is quantified by a number z, the redshift. For small z, the recession velocity is roughly v/cz, where c is the speed of light. In the 1920s, Edwin Hubble and others combined these ideas. They measured distances to galaxies using Cepheid variable stars as standard candles. They measured redshifts from spectra. They found that, on average, more distant galaxies had larger redshifts. That pattern is not random motion. It is a systematic relation. The simplest interpretation is that the universe is expanding. That discovery killed the idea of a static universe in mainstream cosmology. To describe this expansion, we use general relativity, Einstein's theory of gravity. In general relativity, gravity is not a force in the Newtonian sense. It is the curvature of spacetime. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. On the scale of the whole universe, we assume that matter is roughly evenly distributed when we average over very large volumes. That is called homogeneity and isotropy. Under that assumption, the solutions to Einstein's equations are the Friedmann-Lemaitre-Robertson-Walker, or FLRW, metrics. These solutions naturally include expanding or contracting universes. The dynamics of the scale factor AT are governed by the Friedmann equations. They relate the expansion rate HT to the total energy density of the universe, matter, radiation, curvature, and any form of energy associated with space itself. If the universe is filled with normal matter and radiation only, we expect the expansion to slow down over time. Gravity pulls everything together. The expansion can start fast, but it should decelerate. For decades, cosmologists tried to measure how much the expansion was slowing. They introduced a parameter called the deceleration parameter, Q0. The question was, will the universe expand forever, slowly coasting to a stop? Or will it eventually recollapse in a big crunch? To answer that, we needed accurate distances and redshifts for very distant galaxies. That is where Type 1a supernovae became crucial in the 1990s. Two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, collected data on distant Type 1a supernovae. They expected to see evidence of deceleration. Instead, they saw the opposite. The distant supernovae were dimmer than expected. That meant they were farther away than a decelerating universe would allow. The only consistent interpretation, within general relativity and the FLRW framework, was that the expansion of the universe is speeding up. The deceleration parameter was not positive. It was negative. The expansion was accelerating. To explain this, cosmologists revived an idea that Einstein himself had introduced and later discarded, the cosmological constant, usually written as L. In Einstein's equations, L acts like a uniform energy density of empty space. It does not dilute as the universe expands. Its pressure is negative in a specific sense. In relativity, pressure contributes to gravity, not just energy density. A positive cosmological constant has an equation of state parameter W equals P squared equal to -1, where P is pressure and R is energy density. This negative pressure leads to repulsive gravitational effects on large scales. It drives accelerated expansion. We now use the term dark energy as a general label for whatever is causing this acceleration. The simplest model is that dark energy is exactly a cosmological constant. That is the Lie in the LCDM model, our standard cosmological model. CDM stands for cold dark matter. In LCDM, the universe is spatially flat on large scales. Its energy budget today is about 5% ordinary matter, about 25% dark matter, and about 70% dark energy. These numbers come from a combination of observations: supernovae, the cosmic microwave background, and large-scale structure. The cosmic microwave background, or CMB, is the afterglow of the hot Big Bang. It is radiation released when the universe was about 380,000 years old, when electrons and protons combined to form neutral hydrogen, and the universe became transparent to light. We observe the CMB as a nearly uniform microwave glow coming from all directions. Tiny temperature fluctuations in the CMB at the level of 1 part in 100,000 encode information about the early universe, its composition, its geometry, and the seeds of the structures we see today. Satellites like COBE, WMAP, and Planck have measured the CMB in great detail. When we fit the pattern of temperature fluctuations with cosmological models, we find strong evidence for a flat universe with a significant dark energy component. The angular scale of the first acoustic peak in the CMB power spectrum tells us about the geometry. The relative heights of the peaks tell us about the matter content, including dark matter and baryonic matter. The overall fit requires something like a cosmological constant dominating the energy density today. Large-scale structure surveys give another line of evidence. Galaxies are not randomly scattered. They form a cosmic web of filaments, sheets, and voids. The way this web grows over time depends on gravity and on the expansion history. If dark energy is present and causing acceleration, the growth of structure is slowed at late times because the expansion stretches space faster and makes it harder for gravity to pull matter together. By mapping galaxies at different redshifts and measuring their clustering, we can test models of dark energy. So far, the data are broadly consistent with LCDM, though there are some tensions and open questions. Dark matter is a separate but related piece of the story. Dark matter is a form of matter that does not emit, absorb, or reflect light in any significant way. We infer its presence from its gravitational effects. In galaxies, stars orbit the galactic center. If only visible matter were present, the rotation speed should decrease with radius outside the bright disk. Instead, we see flat rotation curves. The outer parts of galaxies rotate faster than visible matter alone can explain. That implies a massive, extended halo of dark matter. In galaxy clusters, we see galaxies moving rapidly within the cluster. We also see hot gas emitting X-rays. The gravitational potential needed to hold the cluster together is much larger than what we can account for with visible matter. Gravitational lensing, the bending of light by mass, provides an independent measure of the mass distribution. In many clusters, lensing maps show mass concentrations that do not line up with the luminous matter. The bullet cluster is a famous example where two clusters have collided. The hot gas, which is most of the normal matter, has been slowed by friction. The dark matter, inferred from lensing, has passed through more cleanly. This separation is strong evidence that dark matter is some kind of collisionless, non-luminous component. Dark matter and dark energy are both dark in the sense that they do not shine, but they are very different concepts. Dark matter clusters under gravity. It helps form galaxies and large-scale structure. Dark energy is smooth on large scales. It does not clump in the same way. It acts as a background energy density that affects the expansion of the universe itself. Dark matter pulls. Dark energy pushes, in a specific relativistic sense. They enter the Friedmann equations differently and leave different signatures in the data. How do we know dark energy is not just a mistake in our understanding of gravity? That is an active area of research. One approach is to modify general relativity on large scales. There are theories like FR gravity, scalar tensor theories, and others that change the relationship between curvature and energy. These can, in principle, mimic the effects of dark energy without introducing a new energy component. But they must also pass all the precision tests of gravity we have in the solar system, in binary pulsars and in gravitational waves. So far, general relativity has passed every test with high accuracy. Modified gravity models are constrained strongly. Some are ruled out. Others remain possible, but fine-tuned. Another approach is to consider dynamical dark energy, where the equation of state parameter W is not exactly -1 and may change with time. In these models, dark energy is often represented by a scalar field, sometimes called quintessence. The field has potential energy and kinetic energy. Its effective pressure and energy density can vary. That would lead to a different expansion history than a pure cosmological constant. We can try to measure W by combining data from supernovae, the CMB, baryon acoustic oscillations, and structure growth. Current measurements are consistent with W equals -1 within a few percent. That does not prove dark energy is a cosmological constant, but it strongly limits how much it can deviate. There is a deep theoretical problem with the cosmological constant. In quantum field theory, even empty space is not truly empty. Fields have zero-point fluctuations. When we calculate the vacuum energy density from quantum fields, we get a number that is enormously larger than the observed value of dark energy. The naive prediction overshoots by something like 120 orders of magnitude. This is sometimes called the worst theoretical prediction in physics. We do not have a widely accepted solution. Some ideas involve cancellations between different contributions, or new symmetries, or anthropic reasoning in a multiverse context. But none of these is universally accepted or supported by direct evidence. From a fundamental physics standpoint, the small but non-zero value of the cosmological constant is a major puzzle. Now I want to connect dark energy to the fate of the universe. In a matter-dominated universe with no dark energy, the future depends on the total density. If the density is higher than a critical value, gravity eventually wins, and the expansion stops and reverses. The universe recollapses in a big crunch. If the density is lower than the critical value, the universe expands forever, but the expansion slows down. It never quite stops, but it coasts. If the density is exactly at the critical value, the universe is spatially flat and expands forever, with the expansion rate approaching zero. With dark energy, especially with a cosmological constant, the picture changes. In LCDM, the universe is spatially flat and dark energy dominates at late times. As the universe expands, the density of matter and radiation decreases because they are diluted. But the energy density of a cosmological constant stays constant. Eventually, dark energy dominates the energy budget completely. When that happens, the expansion becomes exponential. The scale factor grows roughly as A equals EHT, with H approaching a constant value set by Lel. The expansion never slows down. It accelerates. In that scenario, the ultimate fate is a kind of heat death or big freeze. Galaxies that are not gravitationally bound to each other are carried away beyond each other's horizons. Over very long timescales, our local group of galaxies, including the Milky Way and Andromeda, will merge into one large elliptical galaxy. But distant galaxies will recede so fast that their light will never reach us. The observable universe will effectively shrink to our local gravitationally bound region. The night sky will grow emptier of galaxies. Star formation will gradually cease as gas is used up or lost. Existing stars will burn out. White dwarfs, neutron stars, and black holes will dominate. Over even longer times, black holes will slowly evaporate through Hawking radiation. The universe will approach a state that is cold, dilute, and nearly featureless, with a very low rate of interesting physical processes. Dark energy, in the form of a cosmological constant, drives the expansion that leads to this outcome. If dark energy is not a pure cosmological constant, other fates are possible. If W is slightly greater than -1, dark energy still causes acceleration, but its density may change with time in such a way that the expansion history is different. The universe may still expand forever, but the details of structure growth and the timing of events change. If W is less than -1, we enter the realm of phantom energy. In many phantom models, the energy density of dark energy increases with time as the universe expands. That leads to a scenario called the Big Rip. In a Big Rip, the expansion accelerates so violently that in a finite time, it tears apart gravitationally bound systems. First galaxy clusters, then galaxies, then solar systems, then planets, and eventually even atoms could be pulled apart by the expansion. This is a speculative scenario, and it depends on W being significantly less than -1 and staying that way. Current data do not favor such extreme values, but they cannot completely rule them out. There are also scenarios where dark energy decays or changes sign in the far future. It could transition into a different phase, or its equation of state could evolve in a way that causes acceleration to stop. In some models, the universe could even recollapse after a period of acceleration. These ideas are highly model dependent. We do not have observational access to the very far future, so we are extrapolating from limited data. That is why measuring W and its possible time dependence is such a critical goal in observational cosmology. Let me talk about how we measure the expansion history in more detail. Type 1a supernovae give us the luminosity distance as a function of redshift. That is one probe. Baryon acoustic oscillations, or BAO, are another. In the early universe before recombination, the plasma of photons and baryons supported sound waves. These acoustic waves left an imprint in the CMB and also in the distribution of galaxies. They set a characteristic scale, about 150 megaparsecs, in the clustering pattern. This scale acts as a standard ruler. By measuring the apparent size of this BAO feature at different redshifts, we can infer how the expansion has stretched space over time. Weak gravitational lensing is a third probe. Light from distant galaxies is slightly distorted as it passes through the gravitational fields of intervening matter. By measuring the statistical pattern of these distortions, called cosmic shear, we can map the distribution of matter and its growth over time. The growth rate of structure depends both on the amount of matter and on the expansion rate. So lensing helps break degeneracies between matter density and dark energy parameters. Redshift space distortions, cluster counts, and the integrated Sachs-Wolf effect are other tools. Each has its own systematics and challenges. The strength of modern cosmology comes from combining many independent probes. When we do that, a consistent picture emerges: an expanding universe, about 13.8 billion years old, dominated today by dark energy with properties close to a cosmological constant, and by cold dark matter that drives structure formation. Despite this success, there are tensions. One of the most discussed is the H0 tension. The Hubble constant measured from the CMB, assuming CDM, is about 67 kilometers per second per megaparsec. Local measurements using Cepheids and supernova give values around 73. The difference is larger than the quoted uncertainties and has persisted as data have improved. This could be due to unknown systematics in one or both methods, or it could be a hint of new physics beyond LCDM. Some proposed solutions involve early dark energy, a component that behaves like dark energy only at early times and then decays. Others involve changes to neutrino physics or other ingredients. There is no consensus yet. This tension is an example of how dark energy research is not finished. We have a good working model, but we are still testing its limits. Another tension involves the growth of structure, often quantified by a parameter called S8, which combines the amplitude of matter fluctuations with the matter density. Some weak lensing surveys find values of S8 that are slightly lower than what Planck CMB data predict under LCDM. Again, this could be systematics or could hint at new physics, perhaps in the dark sector or in gravity. Future surveys, like the Vera Rubin Observatory's Legacy Survey of Space and Time, the Euclid mission, and the Nancy Grace Roman Space Telescope, aim to improve these measurements and clarify the situation. When we talk about dark energy, we also need to be clear about what we do not know. We do not know the fundamental nature of dark energy. Is it truly a property of space-time, a cosmological constant? Is it a field? Is it an emergent phenomenon? We do not know why its energy density has the value it does. We do not know why dark energy becomes dynamically important roughly at the same epoch when galaxies and stars are well formed. This coincidence problem is puzzling. If dark energy had been dominant much earlier, structure would not have had time to form. If it became important much later, we would be living in a very different universe. Our current theories do not provide a simple, compelling explanation for this timing. We also do not know whether our assumption of large-scale homogeneity and isotropy is exact. Observations strongly supported on scales above a few hundred megaparsecs. But if there were very large inhomogeneities, they could, in principle, mimic some effects of dark energy. Most analyses suggest that such models do not fit the data as well as LCDM, and they often require contrived structures with us near the center, which conflicts with the cosmological principle. Still, testing homogeneity is part of the effort to be sure that dark energy is real and not an artifact of assumptions. On the theoretical side, connecting dark energy to quantum gravity is a major challenge. We do not yet have a complete theory that unifies general relativity and quantum mechanics. String theory and other approaches offer frameworks, but they are not fully predictive in this context. Some constructions suggest that stable de Sitter spaces, which are spacetimes with a positive cosmological constant, are hard to obtain. That has led to debates about whether our observed dark energy can be realized in these theories. This is an area of active research and controversy, and it shows how cosmology and fundamental physics are tightly linked. In summary, dark energy is our name for the observed accelerated expansion of the universe. We infer its existence from multiple independent observations: distant supernovae, the cosmic microwave background, large-scale structure, baryon acoustic oscillations, and gravitational lensing. The simplest explanation, a cosmological constant, fits the data well. It implies that about 70% of the energy density of the universe today is in this form. Dark matter makes up most of the rest, shaping galaxies and the cosmic web through gravity. Ordinary matter is a small minority. We know how dark energy affects the expansion of spacetime. We can write down the equations. We can simulate the growth of structure under its influence. We can predict how the cosmic expansion will continue if dark energy stays the same.